Okay, we next have our next session of faculty talks. We have 3 faculty talks and then our first keynote before lunch.
All right, thank you. Hi, everyone. I'm Renee Zhao, faculty member here at Stanford in mechanical engineering. And today what I'm going to talk about is our recent work on origami robots and how we're developing this robot and translate these robots into endovascular diseases. Medical devices to treat those diseases. So the motivation comes from the existing state-of-the-art disease diagnosis and treatment technologies for minimally invasive surgeries. And if we think about all the navigation and deliverability technologies that these things has, basically are based on tubes, catheters, guidewards, sheaths. These are extremely long, over 1 meter long. These technologies are based on all these long tubes and then inserted either from the mouth or from the leg, from the femoral vein for minimally invasive operations. And the navigation and deliverability, that's the key, but it's very challenging considering a lot of environments are highly tortuous. And the idea of what we're doing here is that we want to develop an untethered system that can actually provide that navigation and deliverability with external magnetic field so that we are getting rid of all the lengthy wires and tubes. So what we recently worked on is to utilize this origami concept. So what we're doing here is that utilize its geometric feature, which shows this propeller-like panels that can generate a propulsion in fluid. In the meantime, its foldability can actually work as a pumping mechanism for targeted drug delivery. So giving you an example here, so this is a roughly 6 to 7 millimeter big small robot, which is controlled by a magnetic field. And what you're seeing here is that it can swim in a water tank. And this, we actually added white particles in the fluid to show the turbulent flow it generated during propulsion. And what is very interesting here is that we are combining the geometric feature of it, which generates the propulsion for swimming. In the meantime, we can use external magnetic field to fold this origami device. And it has actually this internal cavity that can store drug. And then by controlling the folding activity, it can control the amount of drug that is delivered to a specific site. And so we're using this foldability as a pumping mechanism, which is coupled with its locomotion for multifunctionality. And what we want to demonstrate is a very agile locomotion of this amphibious robot. What it can do is that it can roll, it can go through a very complicated terrain surface, and also it can just get into the water. And what's really interesting here is that the internal cavity can be used as a mechanism to store objects. And what we're demonstrating here is that still through a magnetic field, it spins and it can capture objects. The reason is that it generates a suction by spinning. So the mechanism is here. So basically, when it reaches the target, the suction force is generated by the spinning motion, which creates a very low pressure, this deep pressure drop. See over here. So that generates a very low pressure in the cavity that sucks objects in when the object is under spinning. And then we were thinking, okay, so that's a very interesting mechanism combined with this locomotion, right, for navigation and deliverability. And whether we can use this suction mechanism to treat clots. So we did something that is like a toy problem. This is a 5 millimeter robot, and we basically made it swim in a transparent street tube. And we had an artificial blood clot, which is made some random rigid object. And what you can see here is that the robot can swim to the target and then capture it and then take it all the way back with it. But that's actually not the composition of the clot, right? So that's just a very random rigid object. So this is the composition of a clot. The clot is made of fibrin network constraining all the red blood cells. And what we found that's really interesting is that the spinning mechanism actually can interact with the clot in the way that it separates the red blood cell from the clot fibrin network. So basically looking at the SEM images on the left, that's a clot before treatment. And then on the right-hand side, that's the fibrin network, which is highly densified and entangled after treatment. So through this technology, basically we're using the geometric feature of the spinner device to interact with the clot clot. And then in the meantime, what we're doing is to provide shear and compression so that we can separate the red blood cells from the clot and to achieve this highly entanglement of the clot for size reduction. And we actually tested this device performance in our pig studies. So what we're looking at here is that we injected clot in a pig facial artery where we want to test the device performance in highly tortuous environment. And then after treatment, we see this complete opening revascularization of the blood vessel. Eventually, we still really want to develop everything in an untethered manner. So what we are trying to do here is to look at how we can control this really small size robotic system in under magnetic field, how well it navigates in highly tortuous environment, and then eventually how it interacts with the clot for clot removal. And I will stop here, and just one advertisement. We are hiring PhD students and postdocs. If you're interested, feel free to reach out. Thanks.
Okay, thank you. Welcome to Stanford today. I'm happy to talk about our research on feeling our way towards autonomous robotic surgery. So first of all, no bloody pictures in these videos. This is all artificial tissue if you see tissue. So the Da Vinci surgical system, as an example of a teleoperated robotic surgical system, has a surgeon sitting at a console controlling remote robot arms. One of the challenges is that often you would like to have more than 2 arms, and so it's difficult to teleoperate when the human operator only has 2 arms. And one of the things we'd like to do eventually is autonomize a 3rd robotic arm to assist, or maybe even get towards fully autonomous procedures. And these are more than large-scale procedures. You've probably seen examples online of the Da Vinci surgical robot peeling and suturing a grape. We'd like to do dexterous tasks at small scales. But one of the things we think we really need is haptic feedback or touch feedback in this process, both during human data collection, as we did in this non-surgical case in collaboration with Everyday Robots, where we had people train an autonomous system to do a task, and then the learned policy would do better if the person had trained the system with haptic feedback versus without. So we'd like to move this into the surgical domain, recognizing that both vision and touch are important. They have a kind of dual nature where vision is good for some things and touch is good for others. And we feel like systems that are trained only using vision, especially if you're dealing with soft tissues in very critical safety mission critical cases, it will be difficult to do this without haptic feedback. So one of the ways that we've looked at this from the beginning is noting that surgeons can do surgery with robots like the Da Vinci surgical system, even if they don't have haptic feedback. So how do they do that? Well, obviously you get some information from vision. You also get information about the displacement of your instruments through your proprioception and knowledge of your own arms. And so these information come together to give you some estimation, first of all, about what's happening in space, but also about the mechanics of the tissue properties. So you can have some idea of where things are, but then you can also combine your estimates of force and displacement information in order to come up with an estimate of the mechanical properties of tissue. So we wanted to start by, without going towards autonomy, just trying to estimate forces from vision and displacement information alone while doing this through training with a force sensor, even if the force sensor actually doesn't exist on the eventual robot. So we tried this with information from vision as well as robot state together, with the state of the robot only, and then with vision only. And we did a setup like this using artificial tissues in our lab for repeatability with a research version of the Da Vinci surgical system. And this gives just a piece of the data that we collected, showing how as we are palpating an artificial tissue and trying to estimate its tissue properties, you can compare how well we do from a ground truth, from a force sensor underneath the artificial tissue, to different types of techniques that maybe use vision only, state only, and vision and state together. Some more summary data from this is shown here, where we tried to generalize to unseen tools as well as unseen materials and looked at overall what the configurations are. And for most cases, vision alone, interestingly, does better. There's actually some confounding information that comes from the state that we think we can do if we actually have better force sensing on the instruments themselves. So I'll get to that in a minute. But I'll also note that we use these effectively force estimation techniques in order to avoid using force sensing, but actually give haptic feedback to surgeons. So these are actually some examples of teleoperated palpation tasks where in real time we're using our force estimates from vision, state, and in combinations thereof in order to give that feedback. And you can see that some of them are pretty jittery, and it can be hard to stabilize, especially due to some of the delays that it takes in order to implement the force estimation policy. But because one of our issues is that what we would really like to do is collect more detailed force data rather than rely on the state of the robot, which is a little bit iffy, giving flexibility of the system and problems like that. So we've been trying to design some open source force sensors that it can actually go on each jaw of the gripper of a surgical robot like the Da Vinci, but it also applies to many others. So if anyone is interested in trying out our open source force sensing solution, you can take a picture of this QR code here or ask me later. So where we're hoping to go with this is to go towards autonomy, taking this from manual tasks to teleoperated robotic tasks, to actually being able to learn a policy from demonstration. And we're building on the Aloha and other systems that have been developed here at Stanford by my colleagues in computer science. And our long-term goal is to be able to enable more efficient and safer surgery. Thank you.
Hard to be an optimist these days, but I'm trying. And I'll also take note of our very interesting location today. And I also want to say I appreciated the use of Nietzsche's book as an example in one of the student talks earlier today. I think that was very insightful and appropriate. Okay, anyway, so some new work. I want to just really zip through some things. I want to thank the sponsors we're fortunate enough to work with, many of whom are here today. Well, that didn't work. Well, these are a bunch of my students, and these are my students, and many of them are here. That's what I wanted to show. So Chungmin and Lawrence were both presenting posters. And she presented Learf to Go, just this idea of being able to pick things up by inspecting a new representation based on a combination of large language model and NERFs. And the results here are extremely promising. We're very excited about this, and this will be presented also at Coral. We've been doing work on manipulating deformable objects jointly with Toyota, and this project Lawrence will present this afternoon on bagging objects, manipulating plastic bags. Then I want to give a quick update on this work that we're doing with Fleet Dagger. This will also be at Coral, and it's joint with Bosch. Here the idea is that we're looking at the challenge of training robots, fleets of robots that are all performing the same task, where there's a pool of humans and a pool of robots, and the pool of humans is much smaller. And the trick is how to optimally trade off the valuable attention of the humans. And this is an update because we were able to implement this with our FOG ROS system, which is a cloud-based addition to ROS 2. And these are experiments that were performed where the robots are in 2 different buildings, and actually we're performing them as 4 separate robots because the 2 arms are independent, and it's doing pushing tasks that we were able to implement. And we were able to speed this up dramatically and also show that we could develop something called global connectivity, some work by Eric Chen that's joint with Bosch. I want to mention this new thing. We've been very interested in cables, untangling cables for several years. We have a new result that are basically, the challenge is to trace cables here. And the idea is that you're given an image of a cable, and then you want to trace the cable through its crossings. And this can be fairly complex when there's a large number of crossings. I want to show you what ChatGPT 4V does with this. So we asked ChatGPT 4V to untangle the cable, And it happily provided these basically directions of how to untangle it. And then when we plotted it, here's the result. So it's totally unrelated to the real cable, unfortunately. But we're interested in seeing if these kind of things can work. Unfortunately, it's not quite ready for that yet. All right. So anyway, our method is we train two networks. One is to trace and predict the next position of the cable as we go through it. We train it with lots of simulated data. We also train it to classify over and under crossings. And then this is the result. We can generalize. It generalizes fairly nicely to different cables. This is the part I'm really most surprised by, was that if you click on one end of a cable, it will fairly reliably trace that cable through in the presence of other cables. And that, you can see, these can be quite confusing and have many crossings. I also want a quick update. Ambi Robotics is doing well. We're sorting now 1 million packages a week. And come talk to me if you want to know more about that. There's also something new we're working on, which is some of our work on motion planning, where we were finding ways to optimize motions in terms of inertial forces. We were told about this trick that you can turn a wine glass upside down. I recommend trying this with white wine, not red wine. But we were able to implement this in the lab and get the robot to turn the glass completely upside down. But that has resulted in a new company called Jacobi Robotics. And Jacobi is coming out of stealth mode, and if you're interested in that one, talk to me too. The last thing I want to tell you about is something I'm working on with Katie Kwan, who was mentioned in Allison's talk just now. And she and I have been working on this performance with a robot arm. And we're using some of the pose capture tools, and we use that to capture some of her motions, and then have the robot essentially play those back, and then she responds in turn. Then we recapture her motions and use those to fine-tune the robot over time. And we've been doing this for about a year, and then we got an opportunity to perform it. So we're now in rehearsals, and it was her idea. She wants to do it as an 8-hour endurance dance. So it's Katie and the robot. We're calling it Breathless, and it's as 8 hours. It's really about the history of work in America, and you may be familiar with all the time and motion studies that were done historically. That Edward Muybridge his techniques were used to try and optimize the motion of workers. This influenced painters like Picasso and Duchamp. I'm sorry, that was Duchamp. And then these techniques were applied to look at performers, including dancers. And so here's the latest, one of the latest images. We're working with a composer, and it will be at a performance space called National Sawdust in Brooklyn, New York on December 16th, 2023. Thank you.
Any questions for Ken?
Right.
I guess one quick thing I was curious about,
Yeah.
if you don't mind, is you mentioned the kind of cable tracing project. I'm curious what kind of data you had for that and what kind of annotation that required.
No, we used the synthetic data. So we had, basically, they were automatically annotated. We are interested in this idea of annotating data, and I want to mention there something that Justin Kerr developed, which is we call it LOVE, which is learning with ultraviolet. And here the idea is to paint the material with colored ultraviolet light paints that are invisible under natural light, and then you turn off the light, you turn on the ultraviolet, and you get perfect labeling for essentially free, and you can just randomly self-supervise, collect a lot of data. And so we have done that in the past, and so I recommend that. By the way, all of that, the data, the source code, and you can buy all the equipment for that for under $200, and the source code, we have it, and we're happy to share it if you're interested in labeling data fast.
Awesome. Thank
All
you,
right.
Ken.
Thank you, Chelsea.